Good morning, ladies and gentlemen. I'm Akhilesh Lotakia from the Department of Engineering, Science and Mechanics at the Pennsylvania State University. I'm going to talk to you about highly efficient thin film solar cells. But before doing that, let me congratulate you on the Golden Jubilee of the Lalit Narayan Mithila University. And I thank Dr. Ritesh Chaurasia of the Physics Department and his colleagues for organizing this conference as well as for inviting me. I'm going to present some solar cell research that my collaborators and I have performed during the last 5 years. My collaborators include Dr. Faiz Ahmed, who was my PhD student at Penn State and now is a faculty member at ComSats University, as well as Professor Peter B. Monk and Dr. Storm Anderson and Ben Civiletti of the University of Delaware. This research has been sponsored by the U.S. National Science Foundation. But let me begin by contextualizing the research topic. Today, we travel in ultra-fast trains and double-decker intercontinental aeroplanes. Our passenger sea liners are gigantic. These are the technological products of scientific developments that began to take place long before 1990. Propulsion systems, diverse materials, communication systems, electronic devices, vaccines, medical drugs, scientific investigations on these issues had commenced in the 1750s. The year 1990 was a watershed. It saw the emergence of 4 technologies: biotechnology, nanotechnology, information technology, and cognitive technology. Not only those 4, but their confluences and synergies began to usher in Internet of Things, rational artificial intelligence, expert systems, and genetically specific medicines, among other developments. No wonder human population began to grow rapidly during the last 100 years or so. See what has happened in my own lifetime thus far. Human population has doubled, and so has the population of cows, buffaloes, sheep, and goats. This means that we need more energy than ever before. In 2018, the global energy consumption was about 14,000 million tons of oil equivalent. If present trends persist, there will be a 27% increase by 2040 to about 17,500 million tons of oil equivalent. With so much of energy being used for new ways of manufacturing and with new types of devices being used, we will come to a day when most people would not have to work for a living. We can have fun all day and all night. A glorious future awaits humankind. Or does it? The doubling of human population during the last 60 years has been accompanied by a quadrupling of carbon dioxide emission, leading to a 0.8 degrees Celsius change in globally and annually averaged temperature. This is a huge increase. The effects are being felt in our atmosphere, in our hydrosphere, and in our biosphere. These are all interconnected systems. There is a climate emergency. Whether you look at ocean warming, glacier melting, or forest fires, the signs have been incontrovertible for 15 years, except by downright idiots such as Trump and Bolsonaro. What does the future hold for us? The most optimistic prediction is that humans will be wise enough to take immediate and sustained action this year, although very little of this year now remains. Temperature increase will then stabilize at about 2 degrees Celsius above the 1850 level for the next 250 years. The worst projection is a rise of 4.5 degrees Celsius by the year 2100, 10 degrees Celsius by 2200, and 14 degrees Celsius by 2300. Almost all life on our planet will be fried like omelets. This is the crossroads at which humanity finds itself today. A glorious future or death by burning. Our future lies in our hands. The future of other life forms on this planet also lies in our hands. Human civilization must become sustainable. My university's definition of sustainability embraces health, happiness, environment, and future generations, all in consonance with the 1987 Brundtland Report issued by the United Nations. Among other things, we need to examine our energy sources. A desirable energy source must be safe, it must not pollute, it must not deplete resources, and it must be easily accessible and reliable. Today, 85% of our energy needs are met by fossil fuels, which pollute and degrade the environment. Nuclear energy contributes about 4%, but it is not safe. The contribution of wind, solar cells, tides, and geothermal sources is about 4%. Solar photovoltaics contribute slightly less than 1%. That is an astonishingly low figure. As you know, sunlight is converted into electricity by a solar cell. Solar cells were first made in the early 1950s. Today, solar cells made of crystalline silicon are well established commercially. The record efficiency is 26.7%, quite close to the theoretical maximum called the Shockley-Queisser limit. Practical efficiency is about 21%, and the lifetime of solar cells is estimated at 40 years. Solar energy is very clean compared to fossil fuels. Fossil fuels, on the average, produce 160 times more carbon dioxide than solar cells do. Solar energy is the safest of all energy sources. The death rate from accidents and air pollution is 800 times smaller with solar cells than with fossil fuels. Electricity from renewable sources became cheaper during the last 10 years, but electricity from coal and nuclear fuels did not. The cost of solar cells declined by 89%. These solar cells contain crystalline silicon as the photon-absorbing material. Now, every photon that is absorbed generates an electron and a hole. That is how an electrical current is formed. Sometimes an electron and a hole can recombine, and that will lower efficiency of the solar cell. These crystalline silicon solar cells are deployed in solar farms as well as on top of office buildings and houses. Off-grid generation of energy becomes possible, and that is a great blessing because that can minimize transmission losses, which can be as high as 30%. The challenge of solar farms, however, is that agricultural land can be lost. which would have a negative effect on food availability. Even though it is now cheaper to build and operate a solar farm than a new coal-fired plant, solar farms connected to a grid are not enough to meet all human needs. What we need also are electricity generators that are portable and that can be integrated with a device. Each microgenerator should run off solar radiation and or ambient light indoors. It should also be flexible, made of non-toxic earth-abundant materials. Colored solar cells, which will be less efficient, would also fill an important niche. So we need thin film solar cells in addition to crystalline silicon solar cells. Now today, several types of thin film solar cells are available. Gallium arsenide solar cells are more efficient than crystalline silicon solar ones. The rest of the thin film solar cells are less efficient. CIGS and CDTE have about 22% efficiency, and they also have about 5% of the world market. Amorphous silicon and CZT SSE solar cells have half the efficiency of CIGS and CDTE solar cells. They have no market share. Now, gallium arsenide is too expensive for use on Earth. CIGS has three scarce materials: indium, gallium, and tellurium. Cadmium telluride has cadmium that is toxic. Amorphous silicon and CZT SSE have low efficiencies due to high defect densities and low carrier lifetimes. So we must find a way to increase the efficiency and still use a small amount of semiconductor material. That is, we must remain in the thin film format for microgenerators. Peter Monk and I decided to formulate an optoelectronic model to design such solar cells. This is the typical structure of a thin film solar cell. On top is an anti-reflection coating, then comes a transparent electrode, followed by the top passivation layer. Then come two semiconductor layers forming a p-n junction. The first layer is thin, the second layer is thick. Inside the second layer, most photons absorption takes place. Then comes a bottom passivation layer, followed by a layer that serves as both the bottom electrode and an optical reflector. The anti-reflection layer and the bottom reflector trap photons to increase the efficiency. The top and bottom passivation layers retard the recombination of electrons and holes. Our idea was to grade the band gap of the photon-absorbing semiconductor in order to increase efficiency. A solar cell requires optical modeling as well as electrical modeling because it is an optical device as well as an electrical device. But there is a mismatch between the geometric characteristics of the partial differential equations for optics and those for charge carrier transport. Plus, the optics is linear, but charge carrier transport is nonlinear due to recombination. So the mathematical modeling requires two parts. There must be a rigorous optical part and a rigorous electrical part. Peter and I set out to devise exactly that kind of an optoelectronic model. Our idea was to grade the band gap of the photon absorbing semiconductor in order to increase efficiency. I'm not going to take you through the complete model, but I must tell you that the model was used along with the differential evolution algorithm to maximize the efficiency. Details have been published in journal papers as well as in a monograph. I must also point out that the optoelectronic model was validated against experimental data on 7 different solar cells. Let me now present some results. 6 solar cells with a homogeneous bandgap have 22.6% maximum efficiency. Grading, we found out, can increase the efficiency to 27.7%. That is an increase by almost 1/4. For all-gas solar cells, the efficiency increased from 27.6% to 34.5%, again by 1/4. For CZT SSE solar cells, bandgap grading increased the efficiency from 12.6% to 21.7%. That is an increase, an astonishing increase by 3/4. For the 6 solar cell, we found that the small bandgap regions boosted the short circuit current density, whereas the higher bandgap region near the PN junction in the photon absorbing layer boosted the open circuit voltage. For the CZT SSE solar cell, the broad small bandgap regions in the photon absorbing layer have higher electron pair generation rate, and that boosts the short circuit current density. Higher bandgap towards both ends of the CZT SSE layer boosts the open circuit voltage. The same explanations hold for the all-gas solar cells too. Now, the 6 and the CZT SSE solar cells differ only in the photon absorbing layer. We devised a new type of thin film solar cell in which we have both the CIGS layer and the CZT SSE layer. Both can be deposited using the same technology. The materials have a very small lattice mismatch. Both absorber layers are non-linearly graded in this new type of solar cells. This way, a larger portion of the solar spectrum can be captured without the need for additional circuitry used in multi-junction and tandem solar cells. The efficiency shot up to 34.45% according to the model, with improvements in both the short circuit current density and the open circuit voltage. This fantastic results suggests that experimentalists should try to come up with this device in their laboratories. Now, the National Renewable Energy Laboratory has estimated that 0.3 terawatt generation capacity is possible using just rooftop solar cells in USA alone. But that means that the rooftop solar cells shall have to have desirable color and curvature, and they must have a mottled appearance to match roof tiles. Colored solar cells will be less efficient, however, because photons of certain colors will have to be reflected. Efficiency will be reduced by about 10% according to our model if 50% colored photons are rejected. Structurally colored coatings can provide that capability. In summary, bandgap grading can significantly improve the efficiency of thin film solar cells. We hope that experimentalists will take note and soon take up the challenge of making these solar cells. Let me end by introducing all of you to a great man known all over the world for his message of peaceful coexistence. His name was Mohandas Karamchand Gandhi. 80 years ago, he gave a message of sustainability. He wrote, "The earth, the air, the land, and water are not an inheritance from our forefathers, but they are on loan from our children. In your scientific work, please act on his message. Thank you for listening to me.